In this video, we're going to learn about 3 different gas laws, and then we're going to combine them all into the combined gas law in the end. Gas laws are an example of a scientific phenomenon where the law was established empirically through careful experimentation before there was a theoretical explanation made. And so the laws that we're going to look at today between pressure and volume and temperature were established through careful experiments much before the kinetic theory of model of a gas was created. And so a law is an observed phenomenon, and then a theory is an explanation for that phenomenon. And so gas laws are a great example of where we can establish a law without the theory, and the theory can come later. The first one we'll look at is pressure and volume. And so whenever you see a graph that looks like this with a inverse proportionality here, we can say that pressure and volume are inversely proportional. And this was discovered by Boyle in the 1600s through careful experimentation. And practically speaking, how this can help us is we know that pressure times volume would be a constant value. And so this is for a constant temperature and a constant mass of gas, not changing the mass. And if we have a situation where we know the pressure and volume initially, and we want to know the new pressure with the new volume, we can use this type of formula here because we know as long as the temperature and the mass doesn't change, we can use these to establish the new pressure or the new volume. So we're going to look at an example of this. So we have a fixed mass of gas and a volume of 0.6 meters cubed and a pressure of 1.2 times 10 to the 5 pascals. The temperature remains constant. And the gas is compressed until the volume is reduced to this. Calculate the new pressure of the gas. And so this is where we can use that P1V1 equals P2V2. And so for pressure 1, we know that it is going to be 1.2 times 10 to the 5 pascals. And the original volume is 0.60. And that's going to equal the new pressure with 0.20 meters cubed. And if I divide both sides by 0.2, I get the new pressure of 3.6 times 10 to the 5 pascals. One thing to note about this, say the volume had been something different, something other than meters cubed. In this particular case, it's okay to keep them both as the same unit. So as long as they're both the same, it's fine for using this law. Next, we want to use the kinetic gas theory to explain why pressure decreases when volume is increased at a constant temperature. So imagine we have some sort of container that changes volume. So a classic example would be something like a piston. And so we have this fixed mass of gas. So gas cannot enter or escape, temperatures remaining the same. So what's going on here? If I pull this out farther, why would the pressure go down when we increase the volume? And we have to refer back to the kinetic gas theory, and we have to refer to the movement of the molecules. And so if we increase the volume, there is more space for the molecules to move around. And if that's the case, that means there are going to be fewer collisions between the particles, the molecules, and the container. And fewer collisions would lead to a lower pressure. So when we're using the kinetic theory to explain observed macroscopic phenomenon, we have to refer to the movement of the particles. And when we're talking about pressure, we definitely have to mention collisions at some point. So the next macroscopic phenomenon we're going to look at is the relationship between pressure and temperature. And so with a fixed mass at a constant volume, temperature is proportional to pressure. And so proportional means that it is a straight line and it passes through the origin. And so again, through a series of careful experiments, measuring pressure, measuring temperature, this law was established. And for us, in terms of the practical use of this, in equation-wise, is we can use this type of formula here, where the initial pressure over the initial temperature equals the final pressure over the final temperature, if those two are changing, as long as the volume is constant and it's a fixed mass, so there's no losing gas. What they noticed is when they were taking these measurements with the temperature and the pressure, when they were taking the temperature in degrees Celsius, they would extrapolate back and they would go further, and let's see if it got colder and colder and colder, where would the pressure of the gas become zero? And it turns out the pressure becomes zero at a temperature of negative 273 degrees Celsius. And so what this established was the idea of absolute zero, the coldest temperature. And so that is the temperature in which the particles stop moving. And that's where there's no pressure. And so this is why we have the Kelvin scale, because the Kelvin scale is an absolute scale. And so to use this relationship in the previous slide with pressure and temperature being proportional, temperature for us in these gas laws must be in kelvins. So temperature must be in Kelvin because we are using the proportional relationship, and the proportional relationship only goes through the origin with the Kelvin scale. It doesn't go through the origin. 0 degrees Celsius does not represent a pressure of 0. So here we have a fixed mass of gas in a rigid container. So that's the clue there. Rigid container means the volume's not going to change. It's at a temperature of 300 Kelvin, and the pressure is 1 times 10 to the 5. The gas is heated until the temperature reaches 450. Calculate the new pressure. And so we can use that relationship, P1 over T1 equals P2 over T2. And so we have 1.0 times 10 to the 5 over 300 Kelvin. It must be in Kelvin. If this was in degrees Celsius, we would have to convert it. And we want to calculate the new pressure, given that the new temperature is 450 Kelvin. And so if we multiply both sides by 450, we get the new pressure of P2 is 1.5 times 10 to the 5 pascals. Okay, we want to use the kinetic gas theory to explain why pressure increases when temperature is increased at a constant volume. So I'm going to go through this. I'm going to write it in bullet points this time instead of full sentences, but just so we can get the main ideas there. So increase in temperature means an increase in the average, leads to an increase in the average kinetic energy. And since the molecules aren't gaining mass, the only thing they could possibly gain is speed, because kinetic energy is 1/2 mv squared. So the molecules are moving faster. So there's two things that are going to happen with this. One is that there will be more collisions. With the container, which is one thing that would increase the pressure. But also, in the collisions now, there's a greater change of momentum. Because the change in momentum is mass times velocity, or it's in this case speed. And because they're moving faster, there's a greater change in momentum, which means a greater rate of change of momentum. A greater impulse leads to a greater rate of change of momentum, which means there's a greater force. Greater force leads to a higher pressure. So there are actually two things that happen when you increase the temperature. You increase the number of collisions, and then you also increase the force of each individual collision, which leads to a higher pressure ultimately on the container. The third relationship we want to look at is volume and temperature. And with a constant pressure for a fixed mass of gas, no changing in mass, we have volume and temperature being proportional. Very similar to pressure, when they were doing these careful observations, they found that the volume of a gas also becomes zero at negative 273 Kelvin, or sorry, negative 273 degrees Celsius, which led to the adoption of the Kelvin scale being absolute zero. And so similar to pressure and volume, because they are proportional, then when you divide the values, you get a constant. And in this case, that would be the slope of this line. And if we wanted to use that, practically speaking, in a scenario where only the volume and temperature change and pressure remains constant, we can use this type of formula. So we have a fixed mass of gas in a cylinder fitted with a movable piston. So that's the clue that the volume is going to be able to change. And what that does is the pressure remains constant as the volume is changing. So at a temperature of 280, the gas occupies this volume, and then the gas is heated until its temperature reaches 350. Calculate the new volume of the gas. So this is where we want to use V1 over T1 equals V2 over T2, and we can plug in our values here. So we got 0.015 over 280 Kelvin is equal to the new volume over 350 Kelvin, and that gives us a value of 0.019 meters cubed. We're going to do one more explanation here, but again, we're going to reference the kinetic gas model to explain why would the volume increase when temperature is increased at a constant pressure. So if the temperature increased, we went over this in the previous one, but if the temperature increased, that means that the average kinetic energy increases. And I'm going to use symbols now. So the average EK increases, which leads to faster molecules. This leads to an increase in the number of collisions, as well as an increase in the force of each collision. But something happens here that's different than the previous example when we were talking about a fixed volume. So an increase in the force of collisions. So what's happening here is that this container is allowed to move. And so these molecules are going to hit on this container. And if it's allowed to expand like a piston or a balloon or an object like that, the force, instead of increasing the pressure, the force will be used, a change in force will be used to increase the volume or increase the size of the container. So the force and the increase in force and number of collisions leads to expanding the container. So if you have an object that can change its shape, the container will expand. And I will do that in order to keep the pressure constant. So whenever we're doing an explanation of macroscopic things like volume, temperature, and pressure, we always want to refer back to the movement of the molecules and any sort of forces or any sort of things that are increases in speed. We want to be able to describe all of these observations in terms of the kinetic theory or the kinetic model of a gas. And so finally we come to the combined gas law. So a fixed mass of gas, as long as there's no particles leaving the container, gives us this combined gas law for all three. And so this is if the pressure, volume, and temperature change, we can use this law to determine any unknown variables that come later. So let's look at this question here. A fixed mass of gas initially has a pressure of 1.5 and a volume of 0.20 and a temperature of 300 Kelvin. The gas is changed to a new state where the pressure is 1.0, so the pressure has gone down, and the temperature is 360 Kelvin, so the temperature has gone up. And so we want to calculate the new volume of this gas. And so pressure's gone down, temperature's gone up. We can refer back to the combined gas law. So P1V1 over T1 equals P2V2 over T2, and we can plug all these values in. So we have our initial ones, which is 1.5 times 10 to the 5, 0.020, all over 300, and that's going to equal 1.0 times 10 to the 5 times the new volume over 360. And so we're looking at all of our units just to double check. But Kelvin, yep, we want Kelvin. Pascals is good. These are both pascals. This is meter cubed, so my answer that I'm going to get for the new volume is going to be in meters cubed. So I plug this in the calculator and I get a volume of 0.036 meters cubed. Which of the following relationships could be represented by this graph? So this is a proportional graph that goes a straight line going through the origin. Pressure and volume, it can't be pressure and volume. We know that pressure and volume are inversely proportional. Pressure versus temperature in degrees Celsius. Well, pressure and temperature are proportional to each other, so it should be a linear graph. But the Celsius graph didn't go through the origin. So this graph could not represent this relationship. Volume and temperature, we know those are proportional, and it's in Kelvin, so that means it goes to the origin. So this graph could be volume versus temperature. Pressure versus 1 over the volume, so meters to the -3. Well, if we had done an experiment and we had calculated the pressure here in pascals and 1 over the volume, because they are inversely proportional, this graph should be linearized. And so, yeah, this one actually could be this graph here. It could be pressure versus 1 over the volume. Lastly, it's asking us pressure, volume versus temperature. Pressure times volume versus temperature. Well, since we know that PV over T is a constant, yeah, that makes sense. We could have a Y value of PV over an X value of T, and that should give me a straight line through the origin. So this is also an appropriate set of variables for this type of graph. All right, so let's look at this one. When a fixed mass of an ideal gas is compressed at constant temperature, its pressure increases. Which of the following best explains this increase in pressure? So the molecules move with a greater average speed. This one can't be right because it's constant temperature, so that one doesn't make sense. The molecules collide more frequently with each other. That's true, but that doesn't really have anything to do with pressure because pressure comes from collisions with the container. So this is an example. Sometimes you can see multiple choice questions where some things are factually correct, but they don't actually answer the question. Okay, part C, the molecules collide more frequently with the walls of the container. Yeah, that sounds right. And the part D, the molecules remain in contact with the container walls for a longer time. That's not true. Part of our assumptions of the kinetic model is that the collisions time is negligible compared to the time between collisions. So the only one that makes sense in this case is option C.